Hey everyone, and welcome. Today, we are going to pull back the curtain on one of the most brilliant and efficient algorithms in all of computer science, the recursive binary search. Seriously, this thing is the secret sauce that lets your phone and computer find a needle in a digital haystack in the blink of an eye. So, let's start with a crazy question. Imagine you have a digital phone book and it's got over 1 billion names in it, all sorted alphabetically, and you need to find just one. How would you even begin? I mean, are you really going to start at A and just scroll? Well, if you did that, you'd be using what we call a brute force search. And in the worst case scenario, you might have to check 1 billion different entries before you find the one you're looking for. That is just painfully slow. There has to be a better way, a smarter way, right? Oh, yeah, there is. So here's our game plan for today. We're going to start with the core strategy, this idea of divide and conquer. Then we'll see how that translates into recursive logic, with the base case and a recursive step. From there, we'll sketch it out in pseudocode, and then, this is the really cool part, we'll analyze just how ridiculously fast it is. Okay, so the whole secret behind binary search is this amazing concept called divide and conquer. And the best way to get it? Just think about something you've already done 1 million times, looking up a word in a physical dictionary. You don't start at page 1, right? Of course not. You instinctively crack it open somewhere in the middle. You glance at the page. Is your word alphabetically before or after what you see? And just like that, you've thrown away half the dictionary. Then you just do the same thing again with the half that's left. See? You're already an expert at this. All right, let's take that simple dictionary idea and formalize it into the way an algorithm thinks. Now, any recursive solution, and I mean any of them, needs 2 critical parts. A base case, which is its signal to stop, and a recursive step, which is how it keeps making the problem smaller. First up, the base case. You can think of this as the simplest possible version of the problem. For our search, it's what happens when we've divided the list so many times that we're down to just one single item. There's no more dividing left to do. We just have to ask, is this the one we're looking for? This is our stop sign, and it's absolutely crucial. And the second ingredient is the recursive step. This is the divide part of our divide and conquer strategy. We take whatever list we're currently looking at, we find the middle element, and we compare it to our target. Then, based on that one comparison, we call the exact same search function all over again. But this time, we only give it the smaller, correct half of the list. Okay, theory is great, but let's translate this logic into something that starts to look a lot more like actual code. And don't worry, we're going to walk through this piece by piece. So let's look at the logic here. Over on the left, we've got our base case. That's our exit strategy. It kicks in when the search area has shrunk to just one spot. We just check. Is this our item? Yes, great, we're done. No? Oh well, the search is over. Then on the right, you've got the recursive step. If our list is bigger than 1, we find the middle and get ready to chop our problem in half. And this right here, this is where the magic happens. We look at that middle element. Is the thing we're looking for smaller than it? If it is, boom, we throw out the entire second half of the list. Is our target bigger? Then we toss the whole first half. With every single check, we eliminate 50% of what's left. It's so efficient. Okay, so we've got an algorithm that works. But the real question is, how much better is it really? I mean, compared to just checking every single item. To answer that, we got to get into the math and analyze its performance. Now, to measure the speed of an algorithm that calls itself, we need a special kind of equation called a recurrence relation. Don't let the name scare you. All it is an equation that says, hey, the time it takes to solve this big problem is directly related to the time it takes to solve a smaller piece of itself. And that is exactly what our binary search does. Let's build this relation together, step by step. We'll use T of n to mean the time it takes to search in items. First, the base case. That's the easy one. The time to search a list with just one item, T of 1, is just one comparison. Now for any bigger list. What do? Well, we do one little comparison in the middle, let's call that cost plus 1, and then we do the entire process over again on a list that's now half the size. The time for that is T of n divided by 2. And when you put those pieces together, you get this elegant little formula. The time to search n items is the exact same as the time it takes to search n over 2 items plus 1 extra step. This tiny equation perfectly captures the beautiful efficiency of our algorithm. All right, we've got our relation. It's time to solve it and see the incredible, mind-blowing payoff for being so clever. Now, we're not going to dive into the complex math here, but when you solve that relation, you get an answer called O log n, or logarithmic time. Forget the formula for a second. What's important is what logarithmic actually means in the real world, because it means it's fast, like unbelievably fast. And this chart says it all. To find one item in a list of a billion, a linear search could take, well, a billion steps. But binary search, it takes about 30. Not 30,000, not 30 million, just 30. The difference isn't just large, it's almost unimaginable. Just let that sink in for a moment. 30 steps to search a billion items. That's the power of having the problem over and over again. This is why logarithmic algorithms are the bedrock of modern computing. They make searching through these massive, massive datasets feel completely instant. So let's do a quick recap. It all starts with that core strategy, divide and conquer. We build it using recursion, which needs a base case to know when to stop, and a recursive step to keep shrinking the problem. Its performance is captured by that simple relation, T of n equals T of n over 2 plus 1, which gives us that incredible lightning-fast O of log n time complexity. So, I'll leave you with this thought. Binary search isn't just an algorithm, it's a way of thinking. This idea of taking a huge, overwhelming problem and constantly breaking it down into smaller, identical pieces, that's a powerful tool you can use just about anywhere. So where else could you apply this mindset?